Well, let's welcome to, I guess, part one of our engineering project. In this project, we have kind of four pieces of this project, and the whole goal of this is to really show you guys the connection between what you're learning in our math class or what you've learned even in past math classes with what we're talking about specifically in your engineering courses. So it's taking some concepts like, for example, this first project, part one is about linear equations and quadratic equations. So it's taking like those mathematical concepts and relating them specifically to engineering topics like velocity, like currents and circuits, acceleration, spring masses, things like that you're going to be talking about in engineering. And so that's what the whole goal of this like engineering portfolio is, just to kind of link the two together, because if you ever looked at your degree plan or the list of courses you have to have in order to graduate with engineering, it seems like there's just as much math classes as there are engineering courses. So it's really kind of connecting the two and putting that marriage together. Okay? So as we start this kind of part one of the first portfolio, let's kind of just spend 2 seconds reviewing a little bit on the linear equation. We all know our linear equation is basically being y equals mx plus b. Okay, so b is our y-intercept. Okay, or we can also consider that the constant, or we can also consider that like the initial value. Okay, that's all what that back number represents. M is our slope, and it's also, as another definition of slope, it's our rate of change. Ways that we can find slope is the difference in our y values, like y1 minus y2 over x1 minus x2. So it's difference in the y's over the differences in the x's. And the y variables being the dependent variable. Those are the y's. And the independent variable being the x ones. The x's is kind of one of those that it's set there as a given amount of time. In this case, most of the time in engineering, it's going to be time. So it's like in seconds or minutes, and something that we can't really change. It's like when you start a stopwatch, it's going to run. We can't really affect that. Okay? And other than that, the other things we want to know about the linear equation is that the slope on that's constant, obviously, and that if we want to find, let's say, our x-intercept, we know our y-intercept is just going to be b. So to find our x-intercept, then we just put 0 in for our equation. So you can write it as 0 is equal to mx plus b, and that'll get us our x-intercept if we had to find it. Okay, so now that we kind of reviewed just a second, let's go back up and let's start our problems. With this first engineering concept, it's all looking into velocity. Velocity being specifically, by definition, speed in a specific direction. Okay? And in our equation, we're used to, like I said, we usually see y equals mx plus b. So let's connect it here. We have v of t, so the velocity is equal to our initial velocity plus acceleration times time. So y is equal to, the initial velocity is actually going to be b, plus our a is our slope, and our t is our x. Okay? And x, the reason why t is x, or it's like t is our independent variable. Like I said before, it's what we can just kind of start and let it run, and there's nothing that we can affect to it. Its velocity is what changes with respect to time. Okay? Acceleration, if it's positive, it means you're increasing acceleration, and if a happen to be negative, then you're obviously slowing down, you're decelerating. All right, in this first problem right here, we want to determine the initial velocity, so v naught, that's our b, and we want to find the acceleration. So acceleration, that's our slope, the rate of change, and we want to determine our initial velocity, which is our y-intercept, or our v-intercept in this case. If we look at that graph over there, and if you want to label them as y as x, but as you can see, t represents our x variable and v of t our y variable. Okay, and what we do know is the velocity at two specific points. So when the time is 0.75 seconds, then our velocity is 35 meters per second. When we've gone a minute, or 1.25 seconds, a little over 1 second, then our velocity is just 2.4 meters per second. Okay, so we want to determine the initial velocity, and then we want to find the time it takes to stop. Let me graph these 2 points for just 2 seconds for us. at time of 0.75, so there's a quarter, a half, so 3/4 second, or up at 35. So right about there, I guess I would say. And then at 1 1/4 seconds, we're at 2.4, so we're very, very close to hitting that x-axis. Looks like right now they're in a linear pattern, but you never know, it could be a curve. So let's wait and find some other information, then we can come back and graph it. Alright, the first thing I want to find out is, remember, okay, over here on our x-axis is actually our t-axis. So we can call this column our x values, and then we can call this column our y values. Like before, anytime I want to find slope, in this case our slope is our acceleration, and it's the difference in our y value, so it's the difference in our velocity, so 35 minus 2.4 over the difference in our times. Since I did the first minus the second, I'm going to do the first minus the second over here. So 0.75 minus 1.25. And when I plug this into our equation, I get acceleration to be a negative 65.2 meters per second squared. Okay, so that is part of it. We wanted to find acceleration, and now we want to find the initial velocity. Well, if we take our equation so far, our equation thus far, it should be v of t is equal to our initial velocity, which we still need to find, plus our acceleration, which is negative 65.2 times t. So far we found half of our answer. We found the a, we just need to find v naught. Now to get v naught, let's go back, and just like we would normally do with a regular linear equation, let's take a coordinate. Let's say I'll focus more on this first one right here. So let's take 0.75 comma 35. So here's my t value, and here's my v of t, my y value. Let's plug it into our equation. So that'll say 35 is equal to our initial velocity. I'll go ahead and say minus 65.2 times 0.75. Okay. So when we multiply this together and solve for v naught, we get our initial velocity to be 83.9 meters per second. Okay, so now let's go back to that equation we've been building and put it really all together. So the way I can tell velocity at any specific time, it's always going to be 83.9 minus 65.2 times t. So here's our main equation, here's our a, and here's our v naught. Okay. So we've pretty much answered several of the questions. We just need to, the last one we want to know is we want to find the total stopping time. Well, let me go back to the graph for 1 second, because by finding our initial velocity, that 83.9, I have actually found my y-intercept. So let's go ahead and graph that. So this 83.9 is just going to be slightly above that line. And if we connect the dots, try my hardest to try to get all of them, almost, then you can see that that's kind of showing you basically what's happening to this vehicle or whatever object we're looking at that has this for data. We're actually slowing down, obviously. And so we want to find the time to stopping. That's what we're looking for there when they say what's the time to stop. That's our x-intercept. That's what we're trying to find. Okay. Like what we know, anytime you want to find an x-intercept, you go to your equation, you let your y be 0. So 0 is equal to 83.9 minus 65.2t. So, or 65.2t is equal to 83.9. Solve that for t, and you'll get t to be 1.29 seconds. So that's our last part of answer. And if we go up to the graph, if I roughly drew this a little bit, I'm a little off on my numbers right here, but technically it should be kind of right about there, just a little bit past 1.225, our point that we know, but 1.29, and there is our x-intercept, or our t-intercept in this case, since our x-axis represents time. Okay, well, let's go on to a second example.